Much, Josie, and nice to quote unquote see you all again. I will actually be starting off the afternoon series of short talks. So I have a 10-minute summary of the work, my contributions to robotics, and I'm going to focus specifically on our contributions to the AI-driven design of robots and why I think that matters. And then I will hand over the floor to our next speaker. Later this afternoon, I'll be offering a master class where I'll go into some of these topics in a little bit more detail. I just want to double check. Can everybody see the quadruped on the
Perfect.
slide?
It
Perfect.
looks great. Thanks, John.
Great. Okay, so for those of you that don't know me, I started my doctoral work in the group of Professor Rolf Pfeiffer at the University of Zurich. I conducted my doctoral work alongside Fumiya Ida, who was also a PhD student at that time. And when I finished up my doctoral work, I joined Rolf in co-authoring this book called How the Body Shapes the Way We Think. Some of the material in this book is a little dated at the moment, but this was Rolf's and my best attempt to try and summarize why exactly we should think carefully about the physical structure of robots when we go about trying to create intelligent and safe machines that can work alongside us here in the real world. And since that time, I've continued working in this area. This is a snapshot of some of the research projects of my own and from my research group. Starting chronologically in the top left, this was some work I actually did together with Fumiya many years ago now on a brachiating robot. I did my postdoctoral work with Hod Lipson at Cornell University, and you can see the results of that in the top and top right. This was the Resilient Machines project. The middle panel shows some of our relatively more recent work where we've taken this idea of AI-driven robot design and ported it from the AI-driven design of rigid robots to soft robots, which, as many of you know, is a much more challenging area to operate in. But from the perspective of AI-driven design, it's much more interesting because there are much more non-intuitive body plans that can be found by AI that learn how to exploit their interaction with the environment to produce adaptive control. John is always a hard act to follow, but you just heard a lot of examples of how in nature, Mother Nature has found ways to exploit physical structure to produce adaptive and resilient behavior. In the bottom center, that is some of our more recent work on yet another class of robots. So we've gone from rigid robots to soft robots to, in the last few years, biological robots. This is an ongoing research enterprise with Mike Levin from Tufts University. I believe Mike is going to be speaking at this conference. The idea here is, can we build robots from new materials, where in this case we're trying to build autonomous machines from living materials. Lots of advantages. The first is that if you're building from living materials, those living materials have 3.5 billion years of experience of grappling with the real world. So when you build robots out of living materials, you get a lot of adaptive potential already sort of built in, and it's the AI's job to figure out how to reconfigure that material to produce organisms or biological robots that look and act very different from the wild type host organism. Finally, in the bottom right, what you're looking at there is a relatively simple metamaterial. So this is somewhat tangential to robotics, but there's obviously a lot of interesting work going on in soft robotics around the design and use of exotic materials in robots. Exotic materials like soft robots and biological robots are often non-intuitive to work with. And so they, in my opinion, they're a prime target for AI-driven design. So a lot of different projects here. I've tried to arrange them so you can see that there's a common pattern in how we approach all of these problems in robotics, which is to construct a physical simulation of the robot or the material. We then task AI with searching the space of all possible solutions in that space in simulation. And when the search process finds a particularly promising robot design in simulation, we then go to the considerable effort of trying to translate that AI-designed robot from simulation to reality. Sometimes it works, sometimes it doesn't. For all the roboticists here, you already know how difficult it is to cross the reality gap. I'm not going to talk about those technical challenges today. In the 5 minutes that I have left, I wanted to just construct an argument for why we want to go about designing the bodies and brains of robots. One of the reasons, of course, is we are now at the stage where we are starting to deploy increasing numbers of autonomous machines out into the real world, and they are moving in some cases at very high velocity, proximate to human beings. So it is no longer an academic exercise. We need to think very carefully about the design and training of these machines. Most of these autonomous machines are obviously equipped with recent machine learning methods. Very powerful, but they also fail. They may fail rarely, but they still do fail. It's impossible to predict when they will fail, and when they fail, it's impossible to predict how badly their failure will be. You all probably have your favorite examples of this in practice. But this is an increasing motivator for my group to think carefully about how the physical structure of autonomous machines can protect the machine and protect humans against these unexpected failures. So let me try and argue for why the body can help with dealing with out-of-distribution environments, dealing with unknown unknowns. Typically, when we build autonomous machines or any kind of machines as humans, we tend to design something like an automobile and then manufacture very large numbers of that machine. That ends up, what ends up happening then is we have a monoculture of machines. They all have similar or identical form and function. And that is extremely dangerous because if any one of them fails, that failure exists in all of them. Of course, in nature, that's not how nature works. Every single organism on Earth has unique form and function, and there is strength in diversity. So if we can AI design bodies along with brains of robots, that opens the potential for snowflake robotics. We can task AI with designing unique instances of machines. They might all embody the same function, but they do it in a different, using a different form. They all have different shapes and ways of carrying out whatever task we want them to do. So again, to further motivate this idea, I want you to consider this simulated swarm that you see here. It's a relatively simple set of robots. These robots have all been optimized. Their physical structure and their neural control policies have all been optimized. And as you can see, they all embody the same function, which is to move from left to right, but they all do so in very different ways. Here's a more traditional swarm. We have an identical set of instances which all embody the same function, move from left to right, but they have identical morphologies and identical control policies. So we have a heterogeneous swarm, a homogeneous swarm. Let's imagine now that we take these machines after training and introduce them to an unknown environment. For example, they may need to penetrate a cave system and find or extract this useful or interesting or valuable object at the back of the cave. You'll notice that in this case, the homogeneous swarm just doesn't have the right form and function to reach the back of the cave. Our heterogeneous swarm, on the other hand, because it is diverse, it just happens by chance that there is at least one individual that is able to penetrate to the back of the cave and eventually reach this valuable object. It's a simple example, but it's often overlooked that there is this strength of diversity. So one of the things that I'm most interested in embodied intelligence and robotics in the years and decades to come, which is as we increasingly marry state-of-the-art machine learning with state-of-the-art robotics, it opens up new ways to go about approaching the design of autonomous and safe machines. We can, for example, create unique instances of a technology so that they do not share a common Achilles heel. They're not vulnerable to an antagonistic attack. We can always guarantee that at least one member of the aggregate will always be able to exhibit some form of the desired function in new environments, and so on. Just a bit of a plug for why you might want to go about automatically designing bodies and brains, and I will talk a little bit more about this during the masterclass later this afternoon. Okay, thanks very much. I will stop sharing my screen and allow the next speaker to take over.